All right. What we're going to do today is work with WaterGEMS. So open up the WaterGEMS program. Let me give you a copy of the handout, and this is also the assignment description that goes along with this lab. You know, most of the time when we have a lab, you write a report. Sometimes it's a detailed report. Sometimes it's just calculations with a very brief summary of what happened. This time, all you need to submit is screenshots that have brief explanations along with the screenshots. And so the submission burden, I think, is very low for this assignment, and the work itself is fun because it's working with a cool program, WaterGEMS. So what we're going to do during this time that we've got in lab today is I'm going to review a few things with you. We can do it together because it's been a while since you used WaterGEMS. You may have forgotten some of the program features. We're going to go through a typical workflow to set up a flowing fluid demonstration, and then we'll do it for the baseline condition, and then I'll actually just turn you loose to start analyzing these lab activity problems. So we'll do the demo together, and then there will actually be some free time for you to start working on what you need to submit associated with this lab. In the scenario we're going to be considering, we have an elevated water tank, and I don't know if you've ever driven over to the Cincinnati airport, but if you've driven to the Cincinnati airport, you've probably seen this Florence Y'all water tank. It's right off the side of the freeway. It's unmistakable. And we're going to say, what if there was a pipe going directly from an elevated storage tank and it's connected to a hydrant? Now, the hydrostatic equation is what we've considered before. We're just finding what's the pressure at a junction. Now, we're also going to find what's the pressure at a junction, but we're going to do so with having water moving through the pipe. And so now there is going to be energy losses in the pipe as a result of there being flowing fluids. And so in the first assignment you did with WaterGEMS, there wasn't any difference in pressure if the pipe was short versus if it was long. Now there will be, because the water is moving, there's going to be energy losses, and so a long pipe is going to lead to a lower pressure at the outlet than a short pipe will. And the same thing is true of a rough pipe. If you have pipe materials that are rough compared to those that are very smooth, then the rough pipes are going to lead to a lower pressure at the end of the pipeline whenever the water is flowing. So this is exciting stuff. This is exactly what WaterGEMS is designed for, is to quickly and efficiently calculate the pressure in a pipe network under a variety of different flow conditions. So we're going to start with create a new project. And one of the first things that we need to check on when we start a new project is that the unit system is in what we want. And for this one, we're going to use traditional units rather than SI. So go up into Tools, Options, and select the Units tab, and make sure that instead of SI, it says US Customary, and then click OK. After doing that, close the project, don't save the project file, and then start a new one. And then go back up into Tools, Options, Units, and make sure that it says US Customary. So we're starting from scratch with the program already defined as US Customary.
If it opened up in US Customary,
you can leave it if it opened in US Customary. Okay, the next thing is we're going to make sure that the friction method is set to Darcy-Weisbach. Now that's actually going to matter here. When we were working with just the hydrostatic equation in the first activity, it didn't matter if we were using Manning's equation or Hazen-Williams or Darcy-Weisbach. Because as I've told you before, Darcy-Weisbach is the most sophisticated head loss calculating system. It calculates the friction factor as a function of the changing velocity. And you know from your experiment that you designed and conducted that in reality the C value was a little bit different for each of the flow rates. The Hazen-Williams equation assumes that C value is always constant, that flow rate shouldn't change the friction factor. The reason why we're going to bother with Darcy-Weisbach is that The friction factor it calculates specifically for the flow rate in question. And so you get a lot more accurate results with the Darcy-Weisbach. To make it set to Darcy-Weisbach, we go into Analysis, Calculation Options, Steady State / EPS Solver, double click where it says Base Calculation Options beneath it, and then it brings up a list of properties that it's going to use as the calculation options. The property that we want to change is the friction method. By default, it chooses Hayes and Williams. We're going to have it use Darcy-Weisbach instead. Yep. Once you've selected Darcy-Weisbach, then you can close that window, close the calculation options window. Okay, so if you've got the handout here, we're on the bullet point that says Review. We've set unit systems. You put a little check mark next to that. We've set the unit system, and we've set the friction method to Darcy-Weisbach. Next, we're going to draw the network elements. That's something you've done before, but remember, it's this tool right here that we can use to start drawing things, the pipe tool. And so when you click on it, left click, then by default, it's got that little circular symbol there. That means that wherever you click, it's going to lay down a junction. But we want to start off with a reservoir rather than a junction. We look at our picture, it's a water storage reservoir connected by a pipe to a hydrant. So right click, and it brings up a list of different options. Right now it's on junction, but I'm going to choose reservoir instead, and then it changes the symbol next to my cursor. It was a little circle before to represent junction. Now it's showing that trapezoid, which indicates a reservoir. Has everybody got the reservoir? Doesn't matter where you click, but drop it somewhere, and then it connects a pipe to it. And right-click again, and switch it back to junction. We're going to want a junction at the end of our pipe, and then lay that junction down anywhere. It doesn't matter. We're going to use user-defined lengths. You know, where you click does tell the program how long the pipe is, but since we don't have an image in the background here, we're just going to override whatever assumed length it has based on where we clicked, and we're going to enter in what our user-defined length is. And it doesn't matter if it's high or if it's low. This is just a symbolic representation of our pipe network. If you have that junction above the reservoir, it doesn't make any assumption about what the water surface elevations are. This is actually a plan view. This is looking at it from above rather than looking at it from the side. Uh-huh. It's because you were using that symbol. If you use that one, then it gives you the options. Yeah. So I'm seeing lots of personal laptops. I guess that means many of you were able to install WaterGEMS on your own PC. I'm gratified to see that. Okay, so we drew a line. Congratulations to us, right? We are sophisticated. All right, we drew our line. Now let's give it the properties that are defined in this baseline example here. There are a couple of different places we can assign these properties. We can either assign them by clicking on the individual elements or by bringing up the flex tables. So click on this select, the arrow key, and double click on the reservoir. We have to tell it what the reservoir water elevation is. From our Florence Yawl picture, we can see that the elevation is 1,079.37 feet. So I'll go here, scroll down a ways to the physical elevation. That's talking about the water elevation of the tank. And I'll type in 1079.37. That's the hydraulic grade at reservoirs, meaning the water surface. And then I can close it. So now that reservoir has a water elevation. What if I wanted to define the hydrant elevation through the flex table? So I can go to this little symbol here, the flex table. I'm going to click on the upside down triangle to bring up the list of flex tables I can open, and I want to open up the junction table. And here it says elevation, and I'll type in 925.80 and then close it. So I've defined the reservoir elevation. We've defined the hydrant elevation. Any questions so far? Anybody caught on a snag or uncertain why we did a certain thing? One of the lowest evaluations I get each semester on the teaching evaluations is encourages students to ask questions. I'm low on that. I'm trying to improve. I encourage you to ask questions. The other one I'm low on is supportive in academic situations. I don't come across as very supportive. And I don't think I'm ever going to improve that. That's just my personality. I'm not a nice guy. But I do encourage questions. All right? Yeah. You already knew, right?
The first thing you said was
That I wanted to improve supportive?
not supportive of other people
Yeah.
Those are computer science.
Yeah. Too much of an engineer, I guess. Yeah. All right. So we need to define the pipe properties. We haven't yet said how long the pipe is or what it's made out of or what the diameter of the pipe is. And so you can do your choice this time, your choice. Double-click on the element to bring up its properties or open it up in the flex table through the flex table pipe properties. I'm going to do that. So I'm going to scoot over and turn on user-defined length, and then I'm going to input 1,500 feet for the pipe. I'm going to choose, instead of ductile iron, open up the material library and find cast iron. There it is. And change the diameter to 4 inches. Screwed over to the far right, and has user-defined length is an option that you need to click a box to turn on. Yeah, and then you type it in right next to it. Turning on the user-defined length is a little bit harder when you just double-click on the individual element because it brings up so many options. It's hard to find the needle in the haystack sometimes. Did you find the needle in the haystack for the user-defined length?
Yeah, I did that.
Okay. Oh, the flow demand. Yeah, the flow demand we're going to get to in a minute. We haven't done the flow demand yet. So get the length, pipe material, and the diameter set. Good. Has everybody got those pipe properties specified? So if you look at the back side of the assignment, you know, it's going to ask you to analyze a variety of conditions. You know, change the pipe length, change the pipe material, diameter. So the first 3 runs are just varying those properties. The 4th run is varying the flow demand, and the 5th run is varying the liquid. So that's a preview of the assignment that you're going to be doing. Any questions? I encourage questions. Yes?
So, for all these different runs, can you set up different systems with all the same properties?
Okay, he asked a good question. So you could do one of 2 things for your assignment. You could have that, and then you could set up another one that represents condition B and copy and paste another one so that you could actually have 5 different pipes and just execute them all at once. Or you could use this one and change the properties around, execute it, change the properties around, execute it. Either one is fine. It would be easy to copy and paste this system or to draw new ones, you know, or do it sequentially. Either one's fine. All right, so flow demands. How is it that we tell that system that water is actually coming out of the hydrant? The way that you do it is you open up the junction flex table because water comes out of the junction. So we're going to do a demand collection. Now, it's a rotten name for flows coming out of the junction, but we're going to, if you click over here on demand collection, then you'll notice that there's a little dot, dot, dot. Does that have a name? Is that called ellipsis? Little dot, dot, dot. It's got a name. I call it dot, 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 because I can't even count to 3. So click on the 3 dots. There, I did it. And then in demand, type in 180 GPM. You close it, and it's going to know that 180 GPM is being drawn from that junction. And so how is that actually controlled? Well, there's a valve at the junction, and someone is controlling the valve such that 180 GPM is coming out of the junction. And so the question we're asking the simulation is, what's the pressure at that junction when I've opened the valve enough that 180 GPM is coming out? That's the purpose of this simulation, is we want to find out what's the pressure. I already know what the flow rate's going to be. It's going to be 180 GPM. So that's not the independent variable. In this case, the dependent variable is the dependent variable is going to be the pressure. Okay, so now I can click on execute the model, compute, the green arrow. It's already in water at 68 degrees Fahrenheit. But let's review where to do that. That's in the same place that the Hayes-Williams thing was changed. If we go into analysis, calculation options, base calculation options for the steady state / EPS solver, bring that up, scroll down a little bit, then water at 20 degrees Celsius. If we needed to switch over to mercury or kerosene or something, that's where to do that with the ellipsis. All right. So we've calculated the model. If I bring up the junction table, then I can find out what the pressure is. The pressure is 50 psi. And you should have the same pressure within maybe a tenth of a psi, hopefully. $64? Probably your pipe lengths didn't get updated. If it says 64, I'm guessing that your user-defined pipe length isn't set. Let's see if that suspicion is correct. You ever listen to that show Car Talk, where they guess at what people... Oh, it is set, right? All right, did you already do... okay, pipe diameter 6 inches. You need to change the pipe diameter to 4 inches. What's your pipe diameter? Oh, maybe one of the elevations. Did you give elevation to the reservoir? Scroll back up. No, up higher. Elevation there. Yeah, sorry. What's the pressure? Junction. What's your analysis set at Darcy-Wiesbach? Hayes-Williams. Boom. It's probably set on Hayes-Williams rather than Darcy-Wiesbach. So if you go close that, go into the components, or analysis, sorry, the options. Yeah. Hayes-Williams, yeah, switch it to Darcy-Wiesbach. Andrew, you at 50 now? You at 50? What's that?
49.7.
That rounds up to 50. It's kind of annoying to always open up the flex table if you want to know what's happening. So one of the things I'd like to show you how to do is add annotation. So if we're going through this checklist of things that I've demonstrated, we've just done how to specify flow demand at a junction and then execute the model. So here's annotation. Annotation means little words on the map. If on this side, if you expand the pipe, you see it's got label here. I can turn on and off the label. P1 doesn't tell me a lot. I want to add an additional label to that, so I'm going to right-click on the pipe and do New Annotation. All right. I want it to have the length on there. So there's a lot of options it can annotate. And the length that I want it to have is the user-defined length that I've specified. So see here where it says length user-defined, I want to select that. If I click Apply, it puts the length on there, but it's right on top of my pipe, and that doesn't make it very easy to read. Has everybody else done that? Have you put the length on, and it just sort of plops it down right on top of all the other symbology that's already there? Well, we can have it do an offset. See this initial offset thing here? So if I want to offset it in the X direction, that means side to side. How about I'll have it go -10 for the X offset, and I'll have it do +10 for the Y offset, and we'll see where that puts it. So apply, and that's a pretty good spot. Maybe a little bit lower. Maybe that Y offset's too extreme, so I'll do 8. Brings it down a little bit. Let me turn off this OK. I'm going to turn off the label that was there before because that's in the way. And zoom to extents. Okay, so 1,500 feet. You notice it already had the units there. I can right-click in this and edit what I did before. If a prefix is something that's going to go before it, and so if I wanted to have L equals be my prefix and then apply that, then it makes it even more clear that we're talking about a length. So I've got a prefix and the units for a suffix and then the length associated with that pipe length. So I've added a length annotation. Let's also add in a new annotation, new for the pipe diameter. And so from this field name, I have to scroll through all of them and find out which one is associated with the pipe diameter. In this case, it's the one called diameter. And then we'll have D equals be the prefix, and it'll automatically put on the suffix. And I think my Y offset was 8. And this time I'm going to have an X offset of maybe +8. We'll see where that puts me. And not far enough over. Maybe 14. There we go. Better. Okay. So the other thing maybe I'd want to put on there is the material type. So right-click, new, annotation, and then we have to find through here what's the material. Material. And that probably doesn't need a prefix because it's going to say like cast iron or ductile iron. And so there won't be any ambiguity that that's talking about a material. I'm going to put it below the line for that one. I'll put just a Y offset of -8. And that goes below the line there, cast iron. All right. So why don't you annotate 4 additional things. Add a reservoir elevation, annotation, add the junction pressure, flow rate, and elevation. And an example's on the back side if you want to see basically what I have in mind. Go through and add those for the junction and the reservoir. And it's the same process as I demonstrated on the pipe. You just right-click and then do New Annotation. And it brings up the options you need to start adding the annotation for the reservoir and the junction. Which one are you looking for? Yeah. Good luck. Flow rate, it might be demand or, yeah. You know how you can type in the initial offset, like the X and the Y of where you want it to go? Once you've done that, you can also move it around with your cursor. You can just drag it side to side, whichever one is selected, however you prefer. I don't know why all of these junctions are moving though. Huh, that's odd, that's moving all of them. Demand. Flow rate is demand. Yeah. Yeah. Demand. Yeah. You're on the junction, right? Demand. Mm-hmm. Yeah. Yeah, I'll show you how to do a screenshot if you haven't done one before. A what? You can certainly try. But remember, what I want you to do is add some text, like explain how it's changed, what's the effect of what I've described on the pressure, and in terms of fluid mechanics theory, why it's done a certain thing. So what you could do is, there's a key on your keyboard called print screen, and if you just push that key and then you go into Word, then you can paste the screenshot. We'll wait for Word to open. All right, so lab report. So if you just do paste, then it'll bring up that screenshot, and I don't want to see all of it. I just want to see the result, and so you can crop the screenshot. So when you actually click on the screenshot, it brings up these formatting options here, format, crop, and then I'm going to just drag the border down so that it only includes the part that I want to have displayed. And now I can type, you know, the response. And this is the baseline condition. It shows the system. So whatever. You know, if you want to explain all the different things. And so I'll do another screenshot here. So the nice thing about these annotations is that you can change like the demand estimation. If we pull open the junction, remember that I wanted a demand of 180. So what if I change that to a demand of 250 gallons per minute? So I can calculate it, and automatically it updates this. Now I've got the pressures 34 psi. So I can take a screenshot, print screen, go back over here to Word. Control V is another, it's the shortcut for paste. Click on it, format, crop, and then just drag the edges of this down to only include that part that we actually want to show in the report. Solution at Q equals 250 GPM. And then you answer the questions that it has, A, B, C. Yeah.
How do you, like you said, you would copy that 5 times? How do you copy this?
Oh, yeah. I've never done that before. Let's see. Let's see if we can select and then copy. So copy, edit. It might not be possible to copy things. Control C, we'll try it. Control V, no. I guess copying isn't possible, so what you'd need to do is just draw another one. It's a pity that it's not possible because that would really save time. Select all. Yeah. So you'll just have to change them in here and take the screenshot and sequentially paste the screenshots in. Okay, we've got class scheduled until 12:15, and so that gives you about 38 minutes to work on these. You could probably do them all. You might be able to finish the entire lab activity. I'll be circulating around to answer questions if you have any questions, because I encourage that. Yeah?
You go into the WaterGEMS.
Yeah, WaterGEMS.
You draw out a reservoir, and like when you click the end, how do you get that to
Okay, reservoir. So here's my reservoir. Right click. I want it to end in a junction.
Yeah, how do you
Escape.
get before you
Oh, that's cool that it's annotating it automatically.
Yeah.
I learned something new today. I genuinely had no idea that it did that.
You just have to make sure you go back
Huh, wow, I'll be... All right, so I'm going to stop the recording here. By the way, this recording will be posted on MU Online like all the rest of them in case you need to come back and see how to set it into Darcy Wiesbach or change the fluid properties or whatever.